science of astronomy sprang from necessity, the need of the ancients to measure time, to know when to plant and when to harvest. The movements of the moon, the sun, and the stars made it possible. The cycles of the heavens became their celestial calendars. More than 30,000 years ago, a sky watcher carved this remarkable calendar on reindeer bone. Day by day, it seems to show the phases of the moon. A prehistoric etching of the celestial clock, and a harbinger of human preoccupation with time. The point on the horizon where the sun rises each day moves throughout the year. The tilt of the Earth and its annual orbit around the sun create this effect. But twice a year, the sunrise point virtually stands still. Ancient observers recognize these times as midsummer and midwinter, fundamental markers in measuring the seasons. As sunrise began to move again in the other direction, they knew the season was about to change. Around the world, the earliest observers used the sun as a calendar. In this Native American cave, an arrow of sunlight hitting a mark on the wall indicated midwinter. Even older, this Stone Age burial mound in Ireland marks the winter solstice. It's constructed so that the sun shines directly inside, just once a year. It happens every December 21st. On a grander scale, the temples of Abu Simbel in Upper Egypt served as twin markers of the rising sun. But Stonehenge in southern England is the most famous of all. A megalithic observatory par excellence. Its key alignment is here, from the center of the stone circles, through the heel stone beyond, to the midsummer sunrise. A moment of awe. The summer solstice from the heart of an astronomical computer that's been marking time for 5,000 years. To the ancients, the sun and the moon were easily predictable, but the wandering stars were not. The bodies we know today as planets. Planets appear to wander because, like Earth, they're orbiting the sun. They don't move in unison with the background stars. The Greeks saw the universe as a series of concentric crystal spheres, with the Earth fixed at the center. Within each sphere was set an orb. The sun, the moon, are one of 5 known planets. The fixed background stars were set in the outermost sphere. But this neat model failed to explain the eccentric movements of the planets. If they were carried in perfect spheres, why did they sometimes go backwards? The Greek astronomer Ptolemy came up with an answer. Working in Alexandria in the 2nd century, he managed to account for planetary wanderings while keeping the Earth at the center of the model. Ptolemy said that the planets followed epicycles, smaller circles attached to the main spheres. This clumsy notion fit the observations well enough to prevail for 1,800 years. But it didn't stand up to Tycho Brahe's precise observations, or the sun-centered theory of Copernicus in the 16th century. These led Johannes Kepler to discover the key to planetary motion. Kepler's calculations showed that Earth and the planets moved around the sun in slightly elliptical or oval orbits, rather than in perfect circles. Ptolemy's system was finally disproved, and Kepler's calculations also worked for comets and moons. Galileo endorsed the idea and was condemned by the Church. He paid dearly for his pioneering use of the telescope. At the end of the 17th century, Isaac Newton not only split light into the colors of the spectrum, but he hit on the theory of gravity. Newton postulated that gravity pulls an object launched from a mountaintop back to Earth, unless it's got enough velocity, in which case it'll go into orbit, like the moon around the Earth, and the Earth around the sun. With the problem of planetary motion worked out, 19th century astronomers like William Herschel turned their attention to the stars and began mapping the sky. The 20th century would bring huge instruments that probe far into the heavens, taking us further out and further back in time, to a picture of explosive beginnings.
Amazing Space will return on TLC. Amazing Space now continues on TLC.
At the turn of this century, the universe consisted of the Milky Way. Astronomers thought that the strange, irregular patches of light among the stars were just gas clouds in our own galaxy. But when astronomer Edwin Hubble tried to measure the distance to one of those patches of light, he got an unexpected result. He did it by using a kind of star called a Cepheid variable that brightens and dims periodically. Hubble knew that a Cepheid has a useful feature. If you can measure its pulse, you can work out just how far away it is. And the one Hubble observed seemed impossibly distant. A cosmic lighthouse from beyond our galaxy, from a different galaxy altogether. Today, the Hubble Space Telescope monitors ever more distant Cepheids. Hubble continued to study these grand collections of stars called galaxies, and what he found would forever change our view of the universe. He analyzed the light coming from many different galaxies, and he found that in every case, the black lines of the spectrum were shifted toward the red. This cosmological red shift meant that all of the galaxies were moving away from us and each other. There was only one conclusion. The universe was not infinite and unchanging as most had thought. It was expanding. What's more, it must have had a beginning. For if all of the galaxies were rushing away from each other, then at some point in the far distant past, they must all have been roughly in the same place. Scientists traced the history of the universe back to this: a primordial ball of gas, a universe collapsed into a single point, a genesis without dimension. The Big Bang. Time and space rushing outward from some infinitely small point, 15 billion years ago. Now so far flung that miles make no sense. Only light years can hint at the distances to galaxies and the turmoil therein. These pictures of galactic unrest from the Rosat X-ray satellite are windows on the distant past. They took 1 billion years to reach us, so the turbulence they portray happened 1 billion years ago. Galaxies aren't the serene structures we once thought. They bump into one another. Here are two in the process of a gigantic galactic merger. This pair is in a gentler embrace. A computer simulation predicts they'll go their separate ways. In reverse, it's clear how their structures entwine. This picture from the Hubble Space Telescope shows galaxies about to collide. Many scientists now think that these cosmic interactions play an important role in galactic evolution. This galaxy in the constellation of Virgo is pictured in both optical and radio image. The space telescope probed its center and found a surprise. Hubble found a cloud of swirling dust, the signature, scientists think, of a black hole. Like water down a drain, material whirls toward an irresistible center of gravity. Nothing, not even light, can escape. It's a portrait of a black hole, and possibly the heart of our own galaxy. The Milky Way is a good-sized galaxy, bigger than average. Astronomers estimate it contains some 200 billion stars. They orbit the galactic center, among them our own star, the Sun. In isolation, the Milky Way is like a separate universe. But travel away, and it's just one member of a local cluster of galaxies. In turn, these clusters form strands. Like dewdrops on a spider web, each point of light is a cluster. Each cluster contains hundreds of thousands of galaxies. Numbers become meaningless. This is the structure of the universe. Strands of galactic matter strewn through unimaginable emptiness. Technology like the Kobe microwave satellite is revealing the architecture of the cosmos. Kobe took the temperature of the universe, measuring the afterglow of the Big Bang, and confirming that there had been a moment when time and space began. Other satellites are searching for and finding traces of invisible matter. The implication: our universe may someday end, cascading back in on itself in a reverse Big Bang, a cosmic crunch.
Amazing Space will return on TLC. Amazing Space now continues on TLC.
As galaxies are the building blocks of the universe, stars are the molecules in those blocks. But what are stars, and how do they form? Our nearest example is the Sun, a gaseous inferno, a cosmic compromise between nuclear forces straining outwards and gravitational forces pulling inwards, a delicate balance that can't last forever. "15 billion years ago, in the maelstrom of gas and dust that followed the Big Bang, the first stars took shape. They preceded the first galaxies, for without stars, there can't be galaxies. These early stars began to group together. Some may have survived to this day. Globular clusters, as they are called, orbit over the centers of galaxies, galaxies which formed long after the clusters. Seen edge on, the Milky Way has a yellow halo of globular clusters around its center. The ancient stars in these clusters are between 12 and 15 billion years old. Our own star, the Sun, is much younger and lies in a spiral arm towards the edge of the galaxy. Not far from us, we can see stars being conceived in a vast bubble of hydrogen. This bubble lies in a neighboring arm of the spiral, within the constellation of Orion. Inside this cloud of dust and gas, matter is squeezing ever denser. Gravity increases, temperatures soar, nuclear fusion begins, and stars are born. This is a photograph of that stellar nursery, M42, the great nebula in Orion. Recently, the Hubble Space Telescope turned its powerful gaze on these fertile clouds. For the first time, we glimpsed hot new stars, surrounded by great disks of material. In the case of our own sun, such a disk evolved into the planets. The Milky Way is full of places where stars are born. It was in a dark area like this, called a Bach globule, where the sun flared into life. Jolted possibly by a nearby explosion, a cloud condensed to become our star. Settled now into comfortable middle age, the sun shines yellow with a surface temperature of 6,000 degrees Celsius. And that's how it'll be for the next 5 billion years. A nuclear reactor steadily converting hydrogen into helium. But when the hydrogen runs low, our star will begin to die. Desperately, it will start to fuse helium. The sun will change color and begin to expand. Mercury, Venus, and Earth will be consumed. The sun will be a red giant, its nuclear reactor out of control. An unsustainable situation. Finally, its fuel spent, the sun will slowly collapse. And over a prolonged period, the sun will shed material into space. The remaining mass will become a corpse, a white dwarf no bigger than Earth, so dense that a sugar cube of its matter will weigh a ton. Such a relic can be seen in the constellation of Aquarius. It's called the Helix, a nebula wafted out by a dying star. These are the remnants of a more spectacular death, the nebula of a gigantic star blown apart by a cataclysmic explosion. Astronomers call it a supernova. In our own galaxy, many giants are destined to go supernova. One of them is Rigel in Orion, 50,000 times brighter than the sun. And in the same constellation, the great star Betelgeuse. It'll go within the next 10,000 years. Superstars form from superclouds. The process is like the birth of the sun, just bigger. A massive nebula of gas and dust condenses. As it falls in on itself, gravity increases, temperatures soar, and a nuclear furnace ignites at the core. Because it's so big, perhaps 100 times the mass of the sun, the superstar burns fiercely. Enormous gravity at the center creates prodigious heat. As a result, the star fuses a gamut of fuels at an incredible rate. But its life will be short, maybe just 10 million years. In middle age, the giant star spreads. It gets cooler and redder. At the center, helium is fused to create heavier elements. When iron is formed, energy is no longer being created, but absorbed. The red giant collapses. The resulting explosion is a supernova. As material is shed into space, and providing the giant had been big enough, a neutron star remains, just 20 miles wide and spinning once a second. So dense, a pinhead of its material would weigh 1 million tons. There's a neutron star in the Crab Nebula. It can be seen optically, its twin magnetic beams pulsing like a lighthouse. The very largest stars in their death throes collapse beyond the stage of a neutron star to become black holes. A red giant in cross-section reveals the anatomy of a catastrophe. As it ages, the giant fuses more and more elements, not just hydrogen and helium like the sun, but heavy metals. They form internal shells. An iron core is created, only to collapse and explode. Supernovas have seeded the universe. Their catastrophic deaths spread precious elements throughout the cosmos. Precious because without them, there'd have been no blue planet like Earth, no life-giving seas, no breathable skin of air, and no curious beings peering into the heavens in search of the beginning of it all.
The Russian Revolution. It divided East from West and changed the course of human history. Now look back on the days that shook the world, part of This Century, next on the Learning Channel.
You're enjoying TLC's journey through the cosmos, thanks in part to fees paid by your local cable company.
From the highest peaks of the world, great telescopes capture beautiful mysteries, and so can the amateur. But where human eyes cannot see, robots can explore. Take in the view from our many eyes on the universe. Next on Amazing Space.
You're watching the Learning Channel.